Hello and welcome to a fully worked out problem from Chapter 5. In Chapter 5, we talk a lot about the difference between reversible processes and irreversible processes and introduce some ideas about the second law of thermodynamics. So let's get started with a problem that really is extremely valuable since it represents the analysis of a real world situation that you are probably going to encounter in your mechanical engineering career. So let's get started. And I continue to goof around with share screen. So I get confused on how to share screen. So hopefully I'll learn that one of these days. Want to show you how to work out problem 548. And let's look at the problem statement before I give you some sage advice on working through this problem. So here's the problem, and I find this to be it's a classic real-world energy analysis situation that I've been faced with numerous times in my own work. And so I think you're going to find, certainly you're going to find some aspect of this in your upcoming quizzes and tests, no doubt about that. But certainly in your own engineering career, I fully anticipate you're going to be faced with analyzing a situation like this, if not your own home ownership, which I know you aspire to do. Okay, here's the problem statement. It says a heating system must maintain the interior of a building, like your house, at TH equals 20 degrees C when the outside temperature is T sub C, I'll call that T sub L, is 2 degrees C. It says if the rate of heat transfer from the building through its walls and roof is 16.4 kilowatts, determine the electric power required in kilowatts to heat the building using one of three methods. A, electric resistance heating. B, a heat pump whose coefficient of performance is 3. And C, a reversible heat pump operating between those temperature limits, 20 degrees C and 2 degrees C, hot and cold. And so I'm going to show you the solution. I'm going to disclose, how do you solve this problem? First, some remarks. You may read this problem, and I've encountered a good number of students in the past few years, and a good proportion of those students don't know where to start on this problem. And of course, if you've watched some of these videos, you know what I'm going to say next is start with a sketch. However, and I help folks do with that, but they still don't exactly know where to start. So there's two ways that you can approach this from here. We're going to draw a sketch and give you a feel for what's really going on here. It turns out that if you're provided the formulas for parts A, B, and C, this is really an extraordinarily easy problem. So you could skip ahead in this video. You could write down the really only two formulas needed to solve this whole problem and get a good grade on your homework. And that would be great. But if you do that approach, you're not preparing yourself for good performance on quizzes and tests. So that is a way to play it, but I don't recommend it. So what I do recommend is, of course, you try this on your own, draw a sketch, try it all on your own. But if you do get stuck, watch the video, but focus on the fundamentals. Focus on how I try to drag you through the fundamentals first and the order in which you do those fundamentals so that you can see how easy it is. Once you get your fundamentals in place, the computations here are child's play. And this is going to pay off for you in quizzes and tests, but this approach will also really benefit you when you go to graduate school or begin your engineering career. So that's my recommendation. We're all going to start with a sketch. Try to capture the fundamentals, try to understand the fundamentals that I'm going to review with you, and then do the very simple computations. All right, so here's my start with a sketch. A basic visualization of heating a house in the wintertime associated with this project. So here's our house. I've labeled my house TH. Inside is 20 degrees C inside the house. TL, the surroundings, 2 degrees C, and given the heat transfer from the exterior surface of the house to the surroundings is 16.4 kilowatts. That's a perfectly good sketch. Now let's apply Common Sense 101. Common Sense 101 says that in order to keep my house at a constant temperature, keep my house at 20 degrees C, the amount of heat lost from the house to the surroundings has to be made up by some heat transfer into the house, a heat source, that's parts A, B, and C, and that value, that amount of heating has got to exactly be the same amount as what's being lost. That's Common Sense 101, I hope, right? So that makes total sense. I think I got that figured out, but I hope the sketch helps you. This is a must to have the sketch. All right, what's next? Okay. Next is, you're in thermodynamics class and you're trying to sort of teach yourself how to do some thermodynamics speak or engineering speak, okay? And so let's get a little more technical than Common Sense 101. And so here's what I suggest. We'd say your in-house temperature is a constant value at 20 degrees C. In other words, your house is at steady state. Okay, and so think about what you know about the first law already, conservation of energy. It says D capital U of your house, DU of the house, D time, the rate at which the house internal energy is changing is 0. So that mathematical expression says, I've got a closed system, that's my house, and it's at steady state. So that's kind of a neat technical way to talk about Common Sense 101. And so therefore, if we apply the first law, basically, we say, look, we're not, the rate of change of the internal energy is 0. The house is not lifting a weight, so there's no work involved. And so you can say, therefore, Q dot into the house must exactly equal Q dot leaving the house, and it's given in the problem 16.4 kilowatts. And so that's kind of thermodynamic speak of what you got here with this problem. Okay. So now back to our problem at hand. There are 3 options for home heating. And this is where a number of folks, a number of students have gotten tripped up in the past. So I want to make this sort of painfully clear. We've got parts A, B, and C. Electric resistance heating, also known as baseboard heating. Part B, a commercially available heat pump that we can buy off the shelf with a coefficient of performance of 3. And part C, a reversible, also known as a Carnot cycle heat pump. Those are our parts A, B, and C. But the thing for you to realize is all of those parts, they all have 16.4 kilowatts in common. We've got to be supplying 16.4 kilowatts into the house in order to balance the 16.4 kilowatts leaving the house. Hope that kind of makes sense to you. That's kind of a fundamental. All right, let's talk about a basic heat pump. In other words, some details about parts B and C. What I want to do is draw another sketch for parts B and C. Here's my tried and true. If you watch some of my videos, you see that for systems operating a cycle, I have a tried and true schematic that describes a system operating at a cycle at a certain rate between 2 temperatures. And so for our heat pump, here's my yellow, that's my yellow 16.4 kilowatts going into TH, the house, the high temperature reservoir. So I've labeled it inside the house, 20 degrees C, there's my house, okay? And we're transferring heat, 16.4, into that house from a heat pump, a system operating in a cycle. Notice that backwards arrow, the counterclockwise arrow. So this is the system operating in a cycle, and we're transferring heat from the surroundings at a low temperature at the expense of having to add power into our heat pump cycle. So do you see that you've done enough, I hope, system operating in a cycle problems to see that it remains to figure out the power needed to run this heat pump. So that's our objective for parts B and C. How much power is needed to deliver 16.4 kilowatts of heat to the house at TH? Okay, some more fundamentals. What is a basic heat pump cycle in general? So back in general, here's my basic schematic. I've shown in red dashed just to try to get you familiar, get more comfortable with what's a heat pump. Mechanically, the stuff inside this red dash line, that's the mechanical pieces of what we call a heat pump. Won't go into the details of that, but I hope you realize that this sort of black box is the mechanical equipment needed to transfer heat from cold to hot. So it's a closed system, so there's no mass passing across that system boundary. It's a closed system. This closed system is transferring heat at a constant rate from cold to hot. But that would be a violation of the second law if that's all that it took. It requires power in order to satisfy the second law. It requires power to operate this heat pump. So that's a big conclusion. Requires power. So notice here my W dot out is negative, right? W dot net is a number that's less than 0. And then another note that I put in yellow, cold doesn't need to be frigid cold. It could just be the outside surroundings in the wintertime. It could be a cold soil. Could be just about anything that's cool or cold. Okay. Now, hot means it doesn't mean it's got to be extremely hot. It just has to be warmer than cold. And our homework problem is just that, right? Hot is 20 degrees C and cold is 2 degrees C. So in the whole scheme of things, that's not a huge temperature difference, is it? So we've got a classic heat pump problem on our hands. So kind of, I'd say warm and somewhat cold. Okay. Heat pump first law and coefficient of performance. So there's going to be almost enough here to solve the whole problem, but I need to drag you through this. So as a reminder to you, here's my schematic. Remember that for our homework problem, here's my yellow arrow. That's what we're trying to accomplish. That's our goal, is to transfer heat up to TH. The first law for a system operating in a cycle, particularly a heat pump, is the cyclic integral of heat equals the cyclic integral of work. That's a statement of the first law for any system operating in a cycle. Now, you can do the math, and when you study your system boundary, you see that I've got two instances of heat transfer. Here's one heat transfer coming in. Here's one heat transfer going out. So in other words, Qn here is a negative number. And here I've got one instance of work or power going in. And so do you see that W out is going to be a negative number because our arrow is pointing in. And so the other part, if you study on this, you can satisfy yourself that Q dot H minus Q dot L equals W dot net. You shouldn't have to memorize that. You should be able to derive that by looking at your sketch. Notice here you've got two inputs and one output. And so let's say, for example, this output was 3 units. And let's say that this input was 1 unit. 3 units here, 1 unit here. Do you see that almost in your head, you could calculate that this has to be 2 units because I've got 1 unit in, 2 units in, and 3 units out. So that way, you don't have to memorize a formula. You should be able to just sketch the system operating in a cycle and write this down using your eyes. Q dot H minus Q dot L equals W dot net for all systems operating in a cycle. All right, next definition, next fundamental is coefficient of performance for the heat pump. Your textbook calls this gamma of the heat pump. And in words, my professors taught me, and it was so valuable, it's paid off for me 1,000,000 times in my work. In words, the coefficient of performance is the energy sought over the energy that costs. And then it's up to me to figure out what does that mean in terms of a formula. What are we trying to do for a heat pump? We're trying to transfer heat up into a warm space, so the energy sought is Q dot H. That's the energy we're trying to, that's our objective. Now, what does it cost us to run a heat pump? If we own a home or a business, it costs us money to run the compressor of a heat pump. So the energy that costs us money is W.net. That's what costs us. So Q.H over W.net is the coefficient of performance. That's not a formula that you need to memorize. You simply need to remember the coefficient of performance for a heat pump is the energy sought over the energy that costs, and figure it out from there. How about that little example problem? I said that was 3 units. So do you see that that number would be 3 units? And in my example problem, if that was 1 unit, that would be 1. And so for a little verbal example, the coefficient of performance would be 3. It'd be kind of like part B. Okay? I hope that helps. Now we're going to move on to part C, the fundamental for part C. It's a reversible heat pump cycle. A reversible heat pump cycle. That's the same as saying it's a Carnot cycle. And I hope that in your classwork and reviewing chapter 5, you're talking about the Carnot cycle. And what is special about the Carnot cycle is all the processes in the Carnot cycle are fully reversible. There's no irreversibilities for the Carnot cycle. And that enables you in class to derive this relationship that I've got in red. So let's look at the slide. Here's my sketch for the homework problem. Here's my yellow arrow. That's our objective, energy sought, okay? For any, we just talked about the definition of any heat pump cycle. The coefficient of performance is Q.H over W.net. And by the first law, the denominator becomes Q.H minus Q.L, previous slide. And so in your class, you derived a little bit laboriously, is that for a reversible cycle, the temperatures are proportional to the heat transfer. So you can substitute for a Carnot heat pump, which is the maximum coefficient of performance you can get, is simply given by TH over TH minus TL. And you see that you don't have to commit that to memory because you can sort of derive this. You draw a sketch. You can derive gamma, coefficient of performance, is QH divided by QH minus QL, all with dots, okay? And you remember in your mind for reversible cycle, temperature in absolute temperature is proportional to heat transfer. So you've got TH divided by TH minus TL, as long as you remember to keep your temperatures in absolute temperatures, degrees K or degrees R. Now, this gives you as an engineer a powerful tool for quantifying the best possible performance that a heat pump can have and be possible. Otherwise, a claimed coefficient of performance greater than this amount would be impossible. It would be a violation of the second law of thermodynamics. All right, so I've kind of gone on and on about the fundamentals associated with this real world problem. So let's work on part A first. We got a heat pump. We know how much heat we have to dump into our home, 16.4 kilowatts. Determine the electrical power required in kilowatts to heat the building using electrical resistance heating. And there it is. No math is required. All you got to do is go to Lowe's and buy yourself either an electric space heater or electric baseboard heat and turn it on and plug it into the wall and turn it on, and boom, you're heating your house. Okay. These things have one big problem, and that is that an electric resistance heater is a classic irreversible process. Okay. And it's classic because a classic source of irreversibility is transforming work directly into heat. And so that is a big problem that once we finish the numerics of this problem, I'm going to be able to illustrate to you. But that's the one big problem associated with electric resistance heating, is that it is a process that is highly irreversible. Okay, part B. So no math associated with part A. You got your sketch. All right. Part B, determine the electric power required in kilowatts to heat the building using a heat pump with a coefficient of performance of 3. So now we'll just go right back. Here's our sketch that I've kind of beat to death. I've labeled 16.4 kilowatts for Q dot H. I'm given that the coefficient of performance is 3. I remember right from my head, energy sought over the energy that costs. Well, that's Q dot H. That's what I'm seeking to do. W dot net, that's what I've got to pay for. Let's see, Q dot H is known. Here is the math. And so W dot net is going to be 1/3 of Q dot H. And so it's 5.47 kilowatts is the power needed. And so I've written this out in a nice sentence for part B. A heat pump with a coefficient of performance gamma of 3 requires 5.47 kilowatts of electric power to transfer 16.4 kilowatts of heat into the home. Simple. So you do see, if I had just given you this formula, it would take you 2 seconds to get a result, but you would not prepare yourself for a quiz or test. I can assure you that something like this is going to be on your upcoming quiz and tests and probably final exam. So it pays you to try to learn the fundamentals so you don't get tripped up with just saying, oh, this guy gave me the formula. I got a 10 on my homework, and now I'm disappointed that I didn't do well on the quiz or test. We want you to understand the fundamentals. Part C is almost as easy. Part C, determine the electric power required in kilowatts to heat the building using a reversible heat pump. Reversible heat pump. Okay, I'll go back to my fundamental and remember that for a reversible or a Carnot cycle heat pump, the coefficient of performance, gamma, is given by TH over TH minus TL. And the reason is that it is all the processes in the Carnot cycle are fully reversible. And so here's my math. I wrote down my 2 temperatures, and I remembered to transform my 2 temperatures into absolute temperature. Add 273. Everybody knows how to do that. And then you crank through your calculator to get that the coefficient of performance for the Carnot heat pump is 16.28. Wow. Energy sought over energy that costs. And then I go right back then to my definition of coefficient of performance. I know what I know what the needed heat transfer is, Q dot H, 16.4 kilowatts. I wrote that down. I've got 16.28 as my coefficient of performance. And so the power needed is only 1.01 kilowatts. And again, you see how gee, if somebody gives you the formula, it's child's play to get a numerical result. So I've written it out. A Carnot heat pump operating between a home held at 20 degrees C and the surroundings at 2 degrees C only requires 1.01 kilowatts of electric power to transfer 16.4 kilowatts of heat into the home. Wow. Okay, homework done. But let's go an extra mile. Let's go an extra mile and plot out our results. Let's plot out parts A, B, and C on the same chart. And label on the y-axis, let's label the energy that costs, in other words, kilowatts. If you're a homeowner, or you're an engineer running a business, do you see that you're the person that's going to be getting the electric bill for heating your home or your business? And your bill comes in terms of kilowatt hours, and the electric company charges you so many cents per kilowatt hour. Let's say typically maybe 10 cents per kilowatt hour. Okay, well, this is the rate. And so the rate times the time would be kilowatt hour. So you do see that this cost to the homeowner in kilowatts, that's a true cost. That's money out of your pocket. So if you go, and so your job is to keep your home constant temperature, you need to provide 16.4 kilowatts to your house. So if you're running an electric baseboard heating, electric resistance heating, it's going to cost you that much, 16.4 kilowatts, and you got to pay for that. If you go to Lowe's, you can buy a heat pump easily with a coefficient of performance of 3. That's readily available in the real world. And it's only going to cost you 5.47 kilowatts. If somewhere you could buy a Carnot heat pump, and those are few and far between, it would only cost you 1.01 kilowatts to operate that. So you think, well, gee, is this a no-brainer? Man, it's a no-brainer. If I can't get this commercially, my no-brainer is to go with that. Not quite so fast, because as an engineer, there's advantages and disadvantages of things. And this isn't part of your homework problem, is it? But do you see that if you go to Lowe's, you can heat your house with electric baseboard heating for probably well under $1,000. No kidding. Okay. Low installed cost. Okay. But high operating costs. So there's a trade-off there, isn't it? If you buy a heat pump, the installed cost is going to be high, but you're going to save a lot of money in the long run as the years go by in your operating costs. So for example, our heat pump crapped out on us due to age, due to old age, and we had to replace our heat pump in our main in our residence, and it cost $14,000 to replace our heat pump. So that's pretty high installed cost. And so this is going to give you an idea then of the engineering dilemma of what do I select? And it's an engineering study that we don't need to talk about right now. But you get the idea. And also, you get the idea of the value, the real world nature of this homework problem, parts A, B, and C, to really to try to help get you up to speed on what might you be doing in a mechanical engineering career. So very typical of problems that you would have out in the real world. Let's see, if you're still confused a little bit about the Carnot cycle and that how did I change heat transfers into temperatures, I would suggest you go to my Jay's Toolbox YouTube page, look at the cycles, thermodynamics cycles playlist, and then download this Carnot cycle 101 video. Might be worth, if you're still a little confused on that, please have a look at Carnot cycle 101. So what are our conclusions in terms of a recap? Start with a sketch. Wow, you're getting sick of me saying that, but I'm very, very serious. It's going to pay off for you. It's not just like a rule. Plan your work. So rather than simply plopping down formulas that an individual might have given you, like this video, or trying to fish out formulas, plan your work first. Start with the fundamentals. What fundamentals apply to get me to the promised land? In this case, let's see, the first law helped us with that. That was a fundamental, the first law, and the definition of coefficient of performance, that helped us. Energy sought over the energy that costs. And then finally, the Carnot cycle heat pump coefficient of performance that was expressed in terms of temperatures. So those were the three fundamentals that we used to solve this whole problem. Blindly looking for formulas in a book for this problem is particularly tough. And that's why so many students in the past have had trouble getting started with this homework problem, because there's no example problems in the book that really look like this problem. And then the other part is keep your units documented throughout. So for example, on this problem, working in absolute temperature was needed, and also keeping everything in terms of kilowatts was very valuable. So anyway, I hope that helps you visualize that we are giving you homework problems that represent real world situations. They're not just theoretical things where we're trying to torture you. And also, where would you start? After you start with a sketch, what kind of fundamentals are needed to answer the questions that are asked? So hope that helps, and look forward to seeing you in the next homework problem solution.